Hello everyone, welcome to this lecture on equivalence relations. Just to recap, in the last lecture we discussed some special types of relations like reflexive relations, symmetric relations, asymmetric relations, antisymmetric relations, transitive relations. So, in this lecture we will introduce a special type of relation called as equivalence relation, and we will see the definition of equivalence classes. So, what is the formal definition of an equivalence relation? So, it is a relation over a set A which satisfies three properties, namely the relation should be reflexive, the relation should be symmetric, and the relation should be transitive. So, it should satisfy all these three properties. If any of these three properties is not satisfied, the relation will not be called as an equivalence relation. So, let us see an example. So, I define a relation over the set of integers z. So, the set of integers is denoted by this symbol z here, and my relation here is that an integer a will be related to integer b if a is congruent to b modulo m. Okay. So, this is the notation for a congruent to b modulo m. For those who are wondering what is the congruence property here. So, I say that an integer a and an integer b are congruent. So, they are congruent with respect to modulo m if the remainder which I obtain by dividing a by the modulus m is exactly the same as the remainder which I obtain by dividing b by the modulus m. So, m is the modulus here. Okay. Namely the divisor, and you are dividing a by the m and b also by m, and if you get the same remainder, then we say that a and b are kind of equivalent in the sense they have the property that they give you the same remainder when divided by this modulus s, and if that happens we say that a is congruent to b modulo n, and we use this notation. So, the definition of my relation R here is that if any two integers a and b give you the same remainder with respect to some given modulus m. So, the modulus m is given, it is fixed, it is a fixed modulus. Then I say that a is related to b. If you see closely here, the definition of congruence here also mean the following: if a is congruent to b modulo m, then that means that a minus b is completely divisible by m, it gives you 0 remainder. This is because if a modulo m is r and b modulo m is r, then if I subtract b from a, the effect of r and r cancels out, then a minus b will be completely divisible by your modulus m. Okay. Now, my claim is that this relation R is an equivalence relation. It satisfies the property of reflexive relation, symmetric relation, and transitive relation. So, let us prove that. So, is the relation R reflexive? The answer is yes, because you take any integer a, it is always congruent to itself modulo any modulus, because you divide a, whatever remainder you obtain by dividing a by m, the same remainder you obtain by dividing a again by m. So, in that sense a is always congruent to a modulo m. The relation R is also symmetric, we can prove that. So, for proving the symmetric property, I assume that consider an arbitrary pair of integers a b such that integer a is related to integer b. Then as per the definition of relation R, it means that a is congruent to b modulo m. Then as per the definition of congruence, it means that a modulo m is same as b modulo m. Now, I can rewrite this and say that b modulo m is same as a modulo m, and if b modulo m and a modulo m are same, I can say that b is congruent to a modulo m. Okay. So, what I have proved here is, and if b is congruent to a modulo m, that means b comma a is present in the relation R, that means the integer b is related to the integer a as per my relation R. So, what I have proved is, starting with the premise that a comma b is present in the relation R, I can conclude that b comma a is also there in my relation R. That proves my relation R is symmetric. Now, let us prove that the relation R is transitive as well. So, for proving the transitivity property, I have to show that if I have A related to B in my relation and B related to C in the relation, then I have to show that the integer A is related to integer C, and I have to show this for any arbitrarily chosen A B C. So, since A is related to integer B, that means A is congruent to B, or equivalently A minus B is completely divisible by the modulus M. So, I can say that A minus B is some multiple of M, that some multiple is some q1, I am denoting as q1. In the same way, since the integer B is related to integer C, that means integer B is congruent to integer C, or equivalently B minus C is completely divisible by M, or in other words B minus C is a multiple of M, say that multiple is q2. Now, what I can say here is, if I add these two equations here, I get that A minus C is some multiple of M, namely it is q1 plus q2 times M, that means A minus C is completely divisible by the integer M, which in other words means that A is congruent to C modulo M, and if A is congruent to C modulo M, that means the integer A is related to integer C, and that proves that your relation R is transitive as well. Okay. So, that this is that is an example of an equivalence relation. So, now let us define equivalence classes. So, imagine R is an equivalence relation over some set A, and now consider an element from the set A, I am calling it as little a. Then the equivalence class of A, which is denoted by this notation, you have the square bracket and within that you have the element A. So, the equivalence class of little a consists of all the elements from the set A which are related to this element A as per the relation R. Okay. Formally, this equivalence class is a set, it will be a subset of your set A, it will be having all the elements B from the set A such that A is related to B. Okay. That is the equivalence class of an element A, and now this equivalence class satisfies some very nice properties. The first trivial thing to check here is verify here is that you take the equivalence class of any element, it will be non-empty. There will be at least one element which is always guaranteed to be present in the equivalence class of any element A, and that element is the element A itself, right. The element A will always be present in its equivalence class, because the element A is always related as per the relation R, because the relation R is an equivalence relation, and since it is an equivalence relation, it is reflexive. If it is reflexive, every element A is related to itself. So, the element A will always be present in its equivalence class, and hence the equivalence class A will never be an empty set. Okay. So, let me demonstrate what exactly equivalence class looks like with an example. So, I consider this relation R where which is defined over the set of integers, where an integer A is related to integer B if A and B are congruent modulo 3. So, M is equal to 3 here. We already proved in the previous slide that this relation is an equivalence relation. So, what will be the equivalence class of 0? So, equivalence class of 0, so A is equal to 0 here. So, equivalence class 0 will have all the elements B, namely all the integers B, such that 0 is related to those integers B. And it is easy to see that the equivalence class of 0 will be 0, will have definitely 0, because 0 is related to 0, because 0 is congruent to 0 modulo 3. And the equivalence class of 0 will have 3, 6, 9 and these integers, because 0 is related to 3 and you have 0 related to 6 and so on. In the same way, you have 0 related to minus 3, you have 0 related to minus 6 and so on, because 0 is congruent to minus 3, 0 is congruent to minus 6 modulo 3 and so on. So, the equivalence class of 0 will be an infinite set, and it will have all the integer multiples of 3. What about the equivalence class of 1? So, definitely the element 1 will be present in its equivalence class, and apart from that we will have the integers 4, 7, 10 and so on, and on the negative side we have the elements -2, -5, -8 and so on present in the equivalence class of 1, because all these integers are related to the integer 1 as per the relation R. In the same way, the equivalence class of 2 will have the integers 2, 5, 8 and so on in the positive direction, and the elements -1, -4, -7 and so on in the negative direction. Now, if you see closely here, it turns out that the equivalence class of 3 and the equivalence class of 0 and the equivalence class of -3 and so on will be same. That means, the equivalence class of all the integer multiples of 3 will be same. In the same way, the equivalence class of 1, the equivalence class of 7, the equivalence class of -5, namely equivalence class of any integer of the form 3k plus 1 are same and so on. Okay. So, what we are observing here is that even though we have equivalence class of every integer possible here. So, these are the various equivalence classes and this is an infinite list. It turns out that if we closely look here, we find that the two equivalence classes in this sequence are either same or they are completely disjoint. So, for instance, if I consider the equivalence class of 0 and if I consider the equivalence class of 1, there will be no common element. There will not be any integer which is present simultaneously in the equivalence class of 0 as well as in the equivalence class of 1 as per the relation R. You can't have an integer b which is congruent to 0 modulo 3 as well as simultaneously congruent to 1 modulo 3. Whereas, if you consider the equivalence class 0 here and the equivalence class 3, they will be exactly same, they will have exactly the same elements, right. So, it turns out that this property that two equivalence classes are either completely disjoint or they are completely same, it is not present. This property does not hold only with respect to this equivalence relation, this special equivalence relation, it holds in general for any arbitrary equivalence relation, and which is a very interesting property. So, more formally we can prove that if you are given any equivalence relation, any arbitrary equivalence relation over an arbitrary set, then A is related to B if and only if their equivalence classes are same, and their equivalence classes are and the equivalence class A is equal to equivalence class of B if and only if their intersection is non-empty, or in other words, if the intersection of equivalence class of A and equivalence class of B is empty, then the equivalence class A and equivalence class B are different. Okay. And of course, we can prove, we can apply the transitivity property and say that if A is related to B, then the equivalence class of A intersection equivalence class of B will be non-empty. Okay. So, there are two by implications involved here. I am going to prove one of the by implications and I leave the proof for the other by implication for you. It is very simple, it follows the proof of the first by implication. So, I am going to prove this by implication. I will prove that if R is an equivalence relation and if A is related to B, then their equivalence classes are same. Okay. Now, since this is a by implication, I have to prove the implication in both the directions. So, I prove first the implication in the forward direction, namely I assume that A is related to B, and then under this assumption I have to show that their equivalence classes are same. So, since A is related to B, okay. So this is what is given to me, and my goal is to show that the equivalence class of A and B are same. Now, equivalence class of A is a set, equivalence class of B is a set. So, I want to prove here that two sets are equal. So, to prove that two sets are equal, I have to show that they are mutually subsets of each other. That is what is the definition of equality of two sets. So, proving that equivalence class of A is equal to equivalence class of B boils down to proving these two things, that equivalence class of A is a subset of equivalence class of B and vice versa, given that A is related to B. Okay. And how do I prove that a set is a subset of another set? I prove it by showing that you take any element x in the first set, it is present in the second set. So, I take an arbitrary element x belonging to the first set here, the first set here is the equivalence class of A. I have to show that the same x belongs to the equivalence class of B as well. How do I do that? So, since x is present in the equivalence class of A, I can say that A comma x is present in relation R. That means, A is related to the element x, because that is what is the definition of an equivalence class of A. Now, I am also given that R is an equivalence relation, and if R is an equivalence relation, then one of the requirements from an equivalence relation is that it should be symmetric. And if relation R is symmetric and if A comma x is present in the relation R, then x comma A is also present in the relation R as well. Okay. Now, I have x comma A present in the relation R, and as per my hypothesis here, A comma B is also present in the relation R. And since my relation R is transitive, why? Because my relation R is an equivalence relation, the transitivity property ensures that x comma B is present in the relation R. Now, since x comma B is present in the relation R, I can again apply the fact that my relation R is symmetric, because it is an equivalence relation. So, I get that B comma x is also present in my relation R, and if B comma x is present in R, then as per the definition of an equivalence class, the element x is present in the equivalence class of B. That means, starting with the premise that x is present in the equivalence class of A, I have shown that x is present in the equivalence class of B as well, and which proves that the equivalence class of A is a subset of equivalence class of B. And I can apply a similar proof to show that equivalence class of B is a subset of equivalence class of A. So, you start with some arbitrary element x present in the equivalence class of B, and again applying similar steps that we have done here, we have used here, you can show that the same element x will be present in the equivalence class of A as well, and that will show that equivalence class of A and B are same. So, that proves the implication in the forward direction, this we have done. Now, let us prove the implication in the reverse direction. So, assuming R is an equivalence relation and assuming that the equivalence class of A and B are same, I have to show that A is related to B, right. So, for this I start with some arbitrary element x present in the equivalence class of A, then as per the definition of equivalence class of A, it means that A is related to x as per the relation R, and since it is given that the equivalence class of A and B are same, that means the element x will be present in the equivalence class of B as well, then as per the definition of equivalence class, it means that x is related to B as well. If x is related to B, that means if B is related to x, that then I can sorry. So, since B comma x is present in my relation, I can say that x comma B is also present in my relation, okay, because R is symmetric. And why R is symmetric? Because my relation R is an equivalence relation. And now I can apply the transitivity property here on the tuples A comma x and x comma B, okay. So, I have A comma x present in the relation, I have x comma B in the relation, and by applying the transitivity property I get A comma B present in the relation, okay. So, that proves the implication in the other direction, okay. Remember, there is another by implication which I am leaving for you to prove, and that will establish the theorem that we have stated in couple of slides back. So, that brings me to the end of this lecture. Just to recap, in this lecture we introduced the notion of equivalence relation, and we also introduced the notion of equivalence classes. We established the important property that the equivalence classes are either disjoint or they are completely same. Okay. Thank you.